Start today by briefly recapitulating where we were in the last class. We have seen that even though the propositions of Newton were laid the basic framework for deriving differential equations, there were some practical difficulties and we identified the difficulties. Let us enumerate them one by one. The difficulty number 1 was that in a given system, mainly constant system, there will be constant forces. Just to recapitulate what the constants were, there were two types of constants, holonomic constants and non-holonomic constants, and the holonomic constants were those which can be expressed as an algebraic equation, while the non-holonomic constants are those which can be expressed as inequation. So, that was what we did. And then we had said that in order for the body to follow the constraint or constant surface, the constant surface has to apply some kind of a force on it. So, there will always be some force acting on the body, the constant force. And in order to write the Newtonian equation for each body, you will have to take into account all the forces acting on it, and therefore, the constant forces will have to be considered. So, number 1 was the constraint forces have to be considered. So, that was one difficulty, because the constant forces are not always easily quantifiable. The number 2 difficulty was that in an interconnected system, various bodies will interact with each other with forces, and these forces are in general produced by springs. If two bodies are connected by springs, this body will be applying a force on the other body by means of the spring. If two bodies move against each other by means of some kind of frictional element, then one body will apply a force on the other body. So, for each body, these forces have to be considered, and all these forces are vectors. So, that was another difficulty, that the formulation becomes very complicated. So, all the given forces are vectors, and we would like to simplify the matter by writing down the differential equations in terms of things that are scalars. One would be comfortable with that. The third problem was that we have seen that in case of a system with holonomic constraint, for example, the pendulum, it is completely stupid to write 3 differential equations, because it does not move in all the directions. So, in general, if there are n total number of configuration coordinates, no, not n, thrice n. If there are n bodies, there will be 3 times of n number of configuration coordinates, but it is somewhat unintelligent to write all the thrice n equations. Rather, we should be able to write thrice n minus h number of equations, where h is the number of holonomic constraints. So, the number of equations while the number actually required where h is the number of holonomic constraints. So, these were the 3 major difficulties with the Newtonian formalism that we need to overcome. So, let us go one by one. First, let us consider the situation of we consider the situation of the constant forces. 1, how to and in countering this problem we argued that even though the constant forces are there, in general they do no work, because the motion, the actual motion is orthogonal to the constant force. There are situations, somewhat rare situations, most situations the constant forces do not do any work, but where the holonomic constant is what we termed as rheonomic, where the holonomic constant is dependent on time. Say there is a ball in which you have released a marble to move, and the ball is being moved around. So, these are the situations where you have a holonomic constant, all right, but that is dependent on time. Now, when that happens, we need to go into another stage of abstraction. We said that we will not consider the actual motion, actual velocity. We will not multiply the force with the actual velocity, rather we will multiply the force with a specific conceptually or imagined velocity, imagined motion, which is consistent with the constraint at every instant of time. That means, if you have a pendulum with a oscillating support, then at every point the cord has a particular angle and the bob is here. In that case, the admissible motion at that position would be orthogonal to the to the direction of the cord. So, the moment we conceptually imagine that kind of a possible motion, admissible motion, then we have a work. The moment you multiply the forces with that admissible motion, we get a work, but that is not the actual work done by the system, that is again admissible work. You might ask, what gain do we make by considering this? Yes, we do, it will be clear to you later, but what we did was, we said that originally the equation was, originally the Newtonian equation was J is equal to 1 to n, J is the number of mass points, and it was m j r double dot j, that is mass into acceleration term, minus f j, this is the applied force or the given force. This was equal to the constant forces. Okay. So, that was our logic. That was the initial starting point, because this was the what Newton said, and then we said from here that let us multiply both the sides by the admissible displacement. Thereby we got this is a vector, okay, equal to, again the right hand side is equal to 1 to n f c, this is a vector j, times, now this term will obviously vanish, because for each of these n bodies the constant force times the admissible motion is 0. So, is equal to 0. That is how we eliminated the constant forces. So, keep this final equation written in your copy. We will refer to it later. Okay. The second problem was the reduction of the coordinates, and in that what did we argue? We said that after all, in the n dimensional configuration, thrice n dimensional configuration space, each of the holonomic constants define a surface, and if there are two holonomic constants, imagine for the sake of simplicity in visualization, the original configuration space is 3 dimensional, in which you have defined one holonomic constant that will define a surface, right. So, that reduces the dimension by 1. If you have another holonomic constant, that will define another surface. So, ultimately the body will be constrained to move in the intersection of the 2 holonomic constants, and that reduces the dimension by 2. So, each holonomic constant is reducing the dimension by the by its number. Okay. So, since ultimately the body is constrained to move on the intersection of the holonomic surfaces, there is no reason why we should still continue to define the coordinates in terms of the old x, y, z coordinates. We said that okay, now that we have identified a subspace where the body must lie, the configuration point must lie, not the body really, because we are not talking in terms of configuration space. If there are 3 bodies, there will be conceptually thrice n, 3 times 3 number of coordinates, but still I would advise you to still visualize or extend the visualization. We cannot visualize in 9 dimensional space, all right, but still try to extend the visualization, that it is some kind of a space in which the moment you have defined a constant, it defines a conceptually a surface, and the body, the configuration point must lie on that surface, must move on that surface. And therefore, we say that now let us define a new set of coordinates on that constant surface, and these are marked as q, the generalized coordinates. So, in case of the spherical pendulum, what would we do? There is only one body. So, original set of coordinates were x, y, z, and then since the body is constrained to lie on the spherical surface, therefore, on the spherical surface the most convenient coordinates are the spherical coordinates theta and phi. So, we define theta and phi as the new set of coordinates consistent with the constants. Okay. And in a system, there could be some motions that are constant to be on a spherical surface, some motions that are constant to be on a linear side, and in that case those motions will be we try to define the minimum number of coordinates consistent with the constants that completely define the positional status of the system, and that will be the ultimate definition, our definition of the generalized coordinates. So, we said that if we have a original thing like this, and we know that the behavior is constant on this kind of a surface, then we would define a new set of coordinates, and then any point which was earlier expressed in terms of x, y, z, now would have to be expressed in terms of q1 and q2. Okay. Now, extend that vision, this x, y, z could be thrice n, and this q1 and q2 could be again a large number of variables. Just the idea is that we have now defined a lesser number of variables that are consistent with the constants. Clear? So, q's are so, suppose a body was there at this position, then its position is given by this r vector in the original coordinate. Okay. If it is given by the r vector, then for this body, this r was earlier expressed in terms of x, y, z, but now it has to be r has to be expressed in terms of q1 and q2, new set of coordinates. Similarly, there was another body, suppose here its coordinate, say this would be r1 and this one would be r2, and all those bodies coordinates now would have to be expressed in terms of the new set of coordinates, and that can be easily done, because we can say r1 is equal to r1 of the new set of coordinates q1, q2, qn and maybe time. It might also depend on time, because the surface itself might depend on time. Similarly, that will go to Rn, R capital N, Q1, okay. So, in short, we can write then R j jth mass point, this is a vector, as R j of q I and time, where I goes from 1 to n. Now, once we have defined the old set of coordinates in terms of the new set of coordinates, we can also define the velocities. The velocity would be r dot j or d r j dt. So, if r j is dependent on all these, when you take the derivative, it will be expressed in terms of, so you will be able to write and all that, plus the way it depends on time. So, this is nothing but sigma I is equal to 1 to n delta r j vector delta q I, and this is q dot I plus r j. So, this is how the velocity will be expressed, velocity of each body. Fine. Notice in the left hand side what we have, this body is moving, this body's velocity expressed in terms of the new set of coordinates. We will use that. Now, if I ask you, how does the r dot j, this is, so this is r dot j, how does this fellow depend on the generalized coordinates? So, if I ask you del r dot j del q dot I, what do you get? Suppose you want to express this derivative. Look at the right hand side. This is a generalized velocity in one direction I. So, if we differentiate it with respect to another generalized coordinate, you get 0, because its general coordinate is a independent quantity. So, the moment you want to do this derivative with respect to q dot I, then you will find only that term will remain where this and that are the same, all the others will vanish, and this will also vanish, because this tells how does the constant surface vary with time, and that also does not depend on q dot I. So, ultimately what remains is that is it, clear. So, we keep this for future reference. We have argued that this would be valid, and we keep this for future reference. Fine. So, there are two things we are keeping for future reference, one is this equation, another is this equation. We will come back to that. Let us skip somewhere, so that we can again refer to that. Fine. Now, let us get back to this picture. This was the position r of a body. If I ask you what is its admissible motion, its admissible motion is on the surface. So, your admissible motion delta r j, this now has to be on the surface, that now has to be expressed in terms of the new coordinates. And how would you express that in terms of the new coordinates? Exactly the same way. We will say that this is delta r j del q I times delta q I summed over I is equal to 1 to n, right. I mean, I am not writing the broken up form, because that will be the same. For each body j, the derivative of that r j in terms of the ith coordinate times the admissible motion along the ith coordinate. Okay. So, this has to be summed up. So, this is another thing that we keep for future reference. Getting too complicated? No. What we have essentially done is that, what are we interested in? We are interested in the transformation of the coordinates, and who do we transfer? First this vector to the derivative of the vector, that means the velocity, position and the velocity, how do they transform into the new coordinates, and then the admissible motion. That is the three things we wanted to express in terms of new coordinates. That is what we have written down. Fine. Now, let us start with this equation that we wrote. We had multiplied by the generalized by the admissible motion and obtain the right hand side 0. Let us start from there. At this time, our objective is number 2. All the given forces were vectors. So, everything in the Newtonian framework has to be expressed in terms of vectors. And then in any given system, what is the absolutely general scalars that we have? The energies. Energy is a scalar. So, we would like to express, that was the ingenuity of Lagrange, that he said that everything can be expressed in terms of energies. So, let us try to frame the whole set of equations in terms of energies which are scalars. And what are the energies? Kinetic energy and the potential energy. So, that is what we are trying to arrive at, but we will have to go through a route, because the way Lagrange himself did and the way you have to understand, they are a bit different, because now we have the hindsight of how this thing can be derived far easily. That is why we are going this way. So, we start from here. J, there are n number of mass points. So, n m j r double dot j minus f j. I am just copying this. This is a vector, this is a vector, delta r j is equal to 0. That is where we were. Now, we have obtained something about how the generalized admissible motion transforms. We obtained that, and that is what we need to substitute here, the first step. So, we substitute what we have. You can also substitute on your copies, you will see n m j r double dot j minus f j is a vector times all this stuff, I is equal to 1 to n okay. I have just substituted this. Now, there are two summations here and it is immaterial in which order you sum them. So, we bring this summation over I forward. Okay. So, let us do that. We bring this summation over I forward. What remains? What remains are this term. So, you have the summation over j, summation over I. Just to recall, what is summation over I? The number of generalized coordinates, and summation over j is the number of bodies, two things. Then we this term comes m j r double dot j minus f j, okay, this, and then this term delta r j delta q I. So, this term, and then we have to sum over, fine. So, this term is summed over j, and that term after that it is summed over I. Let us put this term inside. So, what do we have? Is this part visible? Yes. I is equal to 1 to n. Let us put this inside. You have sum j is equal to 1 to n m j r vector double dot j times r j delta q I. I have multiplied it here, minus f j vector r delta q I. Okay. Just keep check that I am doing it right. Fine, done. So, we have this term. We need to put a bracket here, because the whole the summation is over the whole thing. Now, let us see what each term mean. What each term means. Here we have r j, that is the position of the nth or jth body, is double dot times this derivative. What does it mean physically? Let us look at it. First, suppose we take r dot j delta r j, these are all vectors. Suppose we start with this term and take a ddt of this. Can you do it? There are two terms here. We will go by the standard way of differentiation. So, we first differentiate this. So, that would be this is dot here, r double dot j times this plus this remains now, and this term is differentiated with respect to time. So, we have r dot. So, del r dot, right, we can do it this way. So, we have just written the derivative like this. Now, you would notice, why did we do all this? Because this term is this term, right. So, this term is expressible as r, this is what we are interested in, expressible as, this is not there, r j del q I is equal to this minus this, r dot j derivative of j with respect to q I minus r j is a vector dot fine. So, we have understood the meaning of the first term in terms of two terms which we are yet to understand, leave it at this stage, but let us substitute it here. Let us substitute it here. What do we have after substitution? We have okay, let us start from further left hand side because it will be rather large. I is equal to 1 to small n, then we have a bracket, then it is in terms of j is equal to 1 to capital N. This is what we are writing m j, then this is substituted. So, it will be m j d dt of r dot j dou r j dou q I, fine, minus, let us break up the summations again, j is equal to 1 to capital N. The next term m j remains. Now comes this term r dot, now this is vector dot j dou r dot j dou q I. So, that substitution is over, but there was another term remaining here that has to be written. So, we will again write it as a separate summation, right here, minus j is equal to 1 to n, it remains as it is, f j dou r j dou q I. Now, this bracket will be closed times your generalized coordinate, generalized admissible motion is equal to 0. Now, after all these business, we have come to 3 terms, one term, second term and the third term, 3 terms, and these just by looking at these terms, it is very difficult to physically understand what they are. So, let us try to physically understand what they are. We will come back to this. So, let us keep this here and let us write down individually. We said that we want to express things in terms of energies. The first energy is kinetic energy. What is the kinetic energy? Total kinetic energy. Kinetic energy expressed written as T. So, kinetic energy is half m v square for each body. So, half m 1 that is r dot 1 square plus half m 2 r 2 vector dot square plus. So, that is the total kinetic energy, that is half, no, I will keep the summation outside, half, this is summed over j is equal to 1 to n number of bodies, half m j r dot j square, fine. Do we have this term around here? No, not really, not exactly this term, but we have what could possibly be obtained from its derivative. So, let us take the derivative of this term, this kinetic energy. So, this is the kinetic energy. So, the derivative of the kinetic energy is after all dependent on the velocity. So, we will take the derivative in terms of the generalized velocity T del q dot I, that is the generalized velocity. If you take, what do you have in the right hand side? We have the summation first, j is equal to 1 to capital N when you take this derivative, this 2 comes forward and gets cancelled with the half. So, it will be m j r dot j and then the derivative of r j del r dot j dot I, right. This is how we would express. Fine. So, we are better off because we can identify this term somewhere here. So, we know that here this term was actually talking about the derivative of the kinetic energy with respect to the generalized coordinate. Good, at least one thing is settled. Now, where did I keep the expressions? Here. See, we have already obtained that the derivative of the velocities would be equal to the derivative of the coordinates. We had already done this. We had kept it for future reference. That is where we will use it. This term is then equal to m j r dot j, but now we do not need to write the velocities, just the positions. Okay. Okay. So, this is something that we will keep, and then let us also differentiate the kinetic energy with respect to the position. So, we have derivative of the kinetic energy with respect to the position, not q dot I, is q I. Then we will again have to write is as the same summation of partial derivatives. So, it will be summation of j is equal to 1 to capital N, and in that case what will remain? M j. See, this is what we are trying to express or take a derivative of in terms of the q I. So, it will be same way, m j r dot j times the derivative of r dot j times the derivative q I. Okay. We can possibly identify that this is this term, right. So, we are slowly homing on to what we wanted to express. Finally, if there is a force, acting on this body, that force, if now we express in terms of the new coordinates, what shape will it take? In the new coordinates, suppose that generalized force is called q I will be expressed as summation of, again j is equal to 1 to n, f, this is a vector, j r vector j. Okay. So, all we are doing, we had the actual forces applied f j. Now, we are transforming into the new set of coordinates q I. So, these are the forces, generalized forces that are applied in the direction of the generalized coordinates. So, this will be the force. Now, suddenly we see that all the terms that we wanted to know, they are all clear. What is this? This is actually the original forces acting on the bodies converted into the generalized forces. What is this? What is this term? This term we have just identified as this term. So, this term is same as this term. So, ddt of this is ddt of this, clear. So, and this term is already we have derived. So, we can now express this equation in a much simpler and elegant form as I is equal to 1 to small n, and then we had written Now, all the summations go away, because this term sum together is some simple term, this term sum together is some simple term, this term sum together is a simple term. So, all these summations go away over J, and we get d dt of del t q dot I, because that is what we had written. This term were expressed as this, and that is what we have in that particular term. So, this is the first term minus the second term here is what we wanted to express. So, we have del t q I, okay, dou t dou q I, that is the second term, and the third term is minus simply q I. This whole thing simple is equal to, sorry, it has to be multiplied by the admissible motion is equal to 0. So, true that we went through a lot of partial derivatives and messy stuff, but ultimately the objective was to simplify stuff, and here is the simple thing. And you notice that here is something that is multiplied by the admissible motion, and the admissible motion along the first coordinate and the admissible motion and the second coordinate are all independent quantities, and this term summed over I would be 0 only if this term is 0 always. Can you see that? So, here is a term for the ith thing, it is multiplied by the ith admissible motion, and all that summed over has to be 0, and that can be 0 only if, since these cannot vanish, this is something that we have assumed that it can be just any motion, therefore, this term must vanish. Okay. Not only that, this term must vanish for all the generalized coordinates, not the summation, just individually along all the generalized coordinates, this term must vanish. So, that gives a very simple equation d dt of dou t dou q I dot minus dou t dou q I minus the generalized forces equal to 0. Now, this is the Lagrangian equation in the most generalized form, in the most general form. You might wonder that so far we were initially talking about energies would be kinetic as well as potential, but so far we have talked out only kinetic energy. So, where does the potential energy come, or where does the potential energy go? Now, you will notice that here we have got a generalized force. What does that mean? It means the forces on the bodies in the direction of the generalized coordinates. So, in case of the pendulum, if you apply a force in the direction of the theta, so that will be the generalized force. Now, what does this force consist of? What could be the different types of forces acting on a body? Just think. So, these are the forces. So, these are the forces that we need to consider. What kind of forces could it be? It could be one, forces like the gravitational force, like the gravitational force. It could be force applied by one fellow on another fellow by means of a spring in between, right. So, a force could be also externally applied, somebody pushes a body. So, externally applied force. and there could be also the force due to friction. So, there could be all these types of forces. Have we taken into account everything? Is there any other type of force that you can imagine that can be applied on a body? No, we have taken everything in. So, if you drop this, the last one, then all the other types of forces are actually derivable from a suitable defined potential energy. I will show that. I will show that, but for this will have to be separately treated. But the other forces, gravitational force, we know that there is something called a gravitational potential, and the gravitational force is the gradient of that potential, we learned in school. But yes, you may not know how that can be done for a force applied through a spring or the externally applied forces, but for now take it for granted. I will illustrate all of these separately. Take it for granted that all these forces can be treated the same way we treat the gravitational force. That means, in the gravitational force we said that there is a gravitational potential, and the force that is applied is actually the derivative of the or the gradient of the potential. So, the potential energy is expressed as V. Is expressed as V. So, the generalized force can be obtained as the gradient or negative gradient clear, and that satisfies your concept of the gravitational force. But in general, in order to visualize, imagine it this way, the potential is like a potential surface. Say, suppose you have got a potential surface like this, and the body. So, this is the qi coordinate, and here is the body, say. So, body's position in qi is this much from here to here. What will be the force acting on the body? The gradient. And you might imagine a 3-dimensional surface. You might imagine a 3-dimensional surface, and in that, if the body's position is such, then the force acting on the body is nothing but the gradient of the potential surface. So, potential is conceptually a surface. You have got the q1 coordinate, q2 coordinate, generalized coordinate, and in that it is a surface, and the position of the body, if you know, then depending on the position it applies a force which is the gradient, and how it also applies to other kinds of forces I will come to, but that at least satisfies your concept of the gravitational potential, does it not? Gravitational potential concept was exactly this. Even electrostatic potentials concept is exactly the same, right? What was the concept of electrostatic potential? That if you have a particular body at a particular place, how much force is applied, and the force is obtained as the gradient of that potential. So, always the potentials concept is the same, that the force is the gradient of the potential, negative of the gradient, like here. How it applies to the other kinds of forces, I will come to that later. But once you assume this, then this can be substituted from there. We will substitute and write d dt I dot minus here we substitute minus dou v dou qi. So, this will be plus now. Lagrange defined a new term called, now it is called Lagrangian. We write it as script L, which is the kinetic energy minus the potential energy. kinetic energy minus the potential energy. So, this can easily be seen that this is a derivative of the Lagrangian with respect to qi. You see that this term, the whole term, but this term, well, here you are taking a derivative of the kinetic energy with respect to the velocity, and the potential is normally not depend on the velocity. So, we can very simply write it as d dt of derivative of the Lagrangian with respect to minus derivative of Lagrangian with respect to. So simple. After all these days labor, we have obtained such a simple equation. That is the actual form of the Lagrangian equation for a non-dissipative system, because we have yet not considered this term. How to consider this term, we will come to that later, but this is the Lagrangian equation for non-dissipative system, for conservative system. Right. Okay, let us stop here and we will illustrate how to apply this to physical systems in the next class.